Recording.
In progress already.
Okay, so first, welcome. I don't know what Andre told you. So I have been working on electromagnetics for the last 3 months. So, you know, I don't know much at all. Haha. Anyhow, as you all know that I've been teaching several lectures at your university before. This course has been taught many times. I've put a special lecture for you together, which actually consists out of 2 lectures. There's one today and one tomorrow evening, same time. And today we are covering borehole methods and petrophysics. And the main topic is how to use electromagnetics for green energy application. And there's going to be a 3rd lecture on geothermal by popular demand from Andre. And I believe this is part of Andre's lecture course. So today I give you the background of material which you probably haven't seen in ever before, so that you understand how to link electromagnetic measurements to borehole measurements. When we start out measuring, we always ask ourselves, are the results that we measure correct? And if we can tie those results to borehole results, we know that they are correct. So that's why I'm going through all of this and explain to you the background. Now, most of you are students in geophysics. Is this correct, Andre?
Yes, it is.
Are there also geology students?
It's only geophysics.
Okay. And this is 1st year, 2nd year?
They are 2nd years. Or 3rd years, actually. 3rd years.
1st year masters or bachelors?
Bachelor students.
Okay.
Sure.
So you can interrupt and ask questions. How much time do I have?
You can have as long as you can present. So it might be 1.5 hours.
I won't need that long because I have a fixed agenda.
Okay.
So we will talk first about borehole geophysics, and I will talk about the background, and then I go into some logging tools and how to tie the borehole measurements to the surface. In the 2nd lecture tomorrow night, we talk about surface methods, and I will explain the methods, equipment, and processing and interpretation of these methods. Now, I have some tools for you. We have a learning center where the lecture will be found, and also a technology library. The username for the learning center is student, that's written down here. And for the technology library, it is EM-book. It doesn't matter whether it's lowercase or uppercase. The passwords are all lowercase, and I will give you the passwords now, so you have to write them down. So the Learning Center password, and I'm going to the Learning Center, is student, and then I'm typing oil is good. So now I'm logging on to the Learning Center. And you can see in the Learning Center, there's a number of courses. There are the lecture courses where you find your lectures. And this is a lecture I was teaching the last 2 weekends. And the lectures go all the way back to 2010.
Of course, we don't see your screen for the.
Oh, I'm sorry. Of course, you
you
don't see my screen because it's on my different screen. So here is the Learning Center. I typed it in. I followed that link. When you go, for instance, to this lecture, there is the presentation, and you can click on it, and then the presentation downloads. It's not supposed to. It's supposed to open. But, you know, you can never get good help. So here, this also is supposed to just open as PowerPoint show. Now this one opens. They all are supposed to just open as PowerPoint show, but anyway, the PowerPoint will open. You can see the lecture. We don't have to go through that. And then Andrew will have to give me your email address and what you're studying and blah, blah, blah. And then you will find your name on the list here. And then you can, in 2 or 3 years, you can click on this and send them emails. Like if I click on this one, I will get into real trouble because this goes to Russia. So then it will start an email client and sends you an email. So that's a learning center. There's also some old term papers and training summaries. There also will be videos in there, but they're not there yet. So then I have given you access also to the technology library, and you click on the technology library. And the username is embook, and the password is great year. One word, lowercase. You click on this and then you get a main collection, and here is a whole number of books, papers that you don't have to search, and you can just click on them. And then the papers come up as PDF file, like this one here, and then you can download it easily. It's all for self-study. So if you want to know what your professor did, you click on this and you look for Pembonan, and you find Pembonan, and there is his master thesis with all of the mistakes and problems that he caused to his thesis supervisor. So he can never hide from you. Takes a second. Here you go. And you can then read his thesis and blackmail him with it, because he did not write this Thai text. He just translated it.
No,
Okay.
I did.
You don't even know how to read and write Thai. Okay, so that's just a resource. I'm sorry, this comes up again. Let's go to the next part. Electromagnetics, or EM, is most commonly used for geothermal, and because of that, it's a green technology. Now, electromagnetics can also monitor carbon dioxide plumes. We all know that with the climate change, we have to take the carbon dioxide out of the atmosphere and where we produce it and inject it back in the ground. And electromagnetics can monitor those plumes. Electromagnetics can also be used for enhanced oil recovery. And if you get 40% more oil out of the ground, you are improving the recovery factor and you're reducing the carbon footprint of oil production. So it is also very important for that. Now, I will also give you an example where electromagnetics is used for special minerals like lithium exploration. And for normal exploration, electromagnetics is a cost reduction and thus reduces the carbon footprint. So this essentially says why electromagnetics is a green technology. Electromagnetics is also important in very critical situations. You all may remember the BP well that was blowing out in the Gulf of Mexico and was spilling every day 1 million barrels per day of oil in the Gulf. And from the very beginning, this is the Macondo well, BP drilled 2 relief wells on the side and then did some steering of these wells and navigation with electromagnetic tools to find this well. They drilled in it and then they pumped essentially cement into the well in order to plug it from the bottom. Next, I will talk about the history of AM methods and the part that is part of the history. Electrical methods were not very popular after the 1980s until marine electromagnetics revived them and used it to find hydrocarbon reservoirs. Electromagnetic methods are a standard technique in borehole measurements. 65% of all borehole measurements worldwide are electromagnetic measurements. In airborne measurements, mining and geothermal. The technology today is well understood. When I was a student of your age, I was hoping that everything that we were learning and working on would actually work. But today we know it works for all of the applications that I'm showing you. So the value today is proven. It's just that it's still not used as much because not very many people know about it. Electromagnetics was invented by the Schlumberger brothers, Conrad and Marcel, in the 1920s. And they were, Conrad was a professor at the mining school in Paris. And they were first looking for minerals in Normandy. And then afterwards, they applied it to the borehole in Alsace. And until 1932, they were providing, as a Schlumberger company, both electromagnetic techniques to oil companies worldwide, mostly in the United States. And then in 1932, there was the financial crisis, and the Schlumberger company ran out of money, and they took a loan from another geophysical company in France. And that geophysical company took over surface measurements, and Schlumberger from 1932 on was only focusing on borehole methods. And that company was called CGG, Compagnie Générale de Géophysique. Now, over the last 50 years, which is of course nonsense, this is a very old slide. I'm older than that. It should be 60 years. Over the last 60 years, magnetotellurics, which is a passive electromagnetic method, is here to stay. And today we have much better instruments. And magnetotellurics uses as source, the signal is coming from electromagnetic signals in the ionosphere. And when those signals are too small, you bring your own transmitter, you generate your own signal, and that means you control your source. And that's called controlled source electromagnetics. And among the controlled source electromagnetics, you have CSAMT, low-TEM, induced polarization, and dipole-dipole methods. The drawback in electromagnetic methods is that the market is too small. Marine work was originally done in the 1980s in the US, Canada, and Russia, and later in Europe. And it was 2000 commercialized by a Norwegian company called EMGS. Today, EMGS is still the only player with a very small business. Marine magnetotellurics is standard, but it's underutilized. And CSEM is more utilized, and it's also standard. There is a time domain version of marine CSEM, also known as TCSEM, but it's not really being used. Induced polarization is used, marine induced polarization is used in Russia and is starting in Norway. Now let's look at geothermal targets. Geothermal targets are coming from the outer core being liquid, molten, and that's indicated with red here. And molten rock is conductive, so it has low resistivity. And at the plate margins, the molten rock comes out to the surface in Hawaii, in Iceland, and of course, there is also Indonesia. And this you can see by looking at the ring of fire. And you can see here that Indonesia is also, Indonesia, which is right here, is also one of the hotspots in geothermal, and hence this strong interest. So Asia has a very large geothermal potential. So does Latin America. Geothermal exploration was originally done, and let me go back to show you. New Zealand is right here. In New Zealand, and in the 1980s, the New Zealanders used many electromagnetic techniques. Since 1980s, magnetotelluric prevails. And I'm getting interrupted. You hear this. There's somebody who wants to watch the lecture. So, Andrew students, here we are now talking about in 1990s, the use of geothermal geophysics was reduced. Today, it's very active and increasing more. And so this interrupt is actually somebody else from Thailand that just woke up. I'll call you back in an hour after the lecture. I call you in an hour. Wait 1 hour. Yes, you can. Bye-bye. Somebody has problems with the internet. Okay, so fixed. I apologize for that. Now the recording has an interrupt from somebody in Thailand having internet problems. So CSEM is now starting to be used. Magnetotellurics is the standard. Now for hydrocarbon applications, in this slide, we have the high value targets. Of course, subsalt is very important, but also in combination with directional drilling. And directional drilling, you want to know where the oil is and where the water is, but also in production monitoring, when you are producing a well and you are sucking out the water to higher and then start producing water. And there are many different methods used. This is the application for so-called special minerals. They're called special minerals because they are important for the green applications. And we are talking about lithium, but also other minerals. And here is a picture from Argentina. The Golden Triangle, Chile, Argentina, and Brazil are covering the largest part of a large Chile, Argentina, Brazil, yeah, the largest part of the lithium deposits. And what you have is you have essentially a salt flat, and the salt water, the brine, gets mixed with minerals from the mountains, and these minerals generate lithium, which is very conductive. So what you see in those cases, you see very conductive layers like here on the right. There's 2 brine layers, and these brine layers have the conductivity of seawater. Of course, at 300 meters depths or 1.5 kilometers depths, you have no seawater in the earth. So this is the lithium, which is very conductive. We have observed similar conductivities in Saudi Arabia, and we suspect lithium there as well. So this is not the only place. There will be many more countries adding to it. In fact, very recently, like 2 days ago, there were reports that they are also starting lithium exploration now in Germany. So the mixture of the mountain minerals and the water in a salt flat, which then evaporates, accumulates this very conductive material. Now, in the past, we would measure physical properties of the rocks. And if you were a very smart geologist, you would look at the physical properties and you would come up with an image of the subsurface and you would drill and you would find oil. But not all geologists are very smart geologists. And so the opportunity arose for the geophysicists to make a multi-billion-dollar industry, mostly geophysical processing. And it's the biggest scam. I mean, it's just like some magic trick. How to come up with a subsurface image. So we essentially have field data measured at the surface and well logs. And then the geophysicists made a complete science around it and a multi-billion-dollar industry. And of course, a good a geologist can go straight from the image by just looking at this data directly to the subsurface picture. Now, in the future, we are looking at monitoring. That means we are looking at time changes of measurements. And when we look at time changes, this entire workflow disappears. And so we're essentially starting with a surface data set and repeat measurements and baseline measurements, followed by the goal to be in compliance with the subsurface requirements. That means the in the CO2 sequestration case, where we are putting the CO2 in the subsurface, we have to make sure that the CO2 doesn't leak out. We need to know how much we put in. We then have borehole measurements, and you need to verify these measurements to be in compliance with the dynamic image. And all of this is then linked with surface data and the image verification. And again, the borehole and the surface is linked with borehole geophysics. So what I tell you today is extremely important to link our surface measurements to the subsurface. So first, let's start with the electrical properties of rocks. We start out with the field measurements, and then we process the data, and we obtain then physical parameters like the resistivities. These are resistivities RT and RXO for borehole measurements. And then we translate those to so-called petrophysical measurements. And these petrophysical measurements are water saturation and porosity. And we are after those petrophysical parameters. And they also not only include porosity, but they also include permeability, which are flow rates, and also the special internal surface of the rocks. Now, when we look at a rock, we have usually, because of the weight, so-called gravity, we have the gravity at the bottom, the gravity. Because of the gravity, we have the small pebbles at the bottom and the large pebbles at the top. And this gives us automatically some layering. You can see we have a layer here, we have a layer there, and this is then a coarser layer. So the deposition by rivers and runoff from mountains gives you automatically layering. And layering leads to anisotropy in a transverse isotropic direction. That means in the horizontal direction, it is isotropic, but in the vertical direction, it's anisotropic. So let's explain those parameters. We have an isotropic model, and the isotropic model, we obtain an isotropic model when the physical parameter does not change with steps. So here, the parameter is in all directions the same. Unfortunately, geophysicists are very poor in coming up with realistic models. So the isotropic model is still today the most common model. It is not realistic. It is unrealistic. Then this is sand. We add gravity to it. And everywhere we have gravity or weight or compaction from the top, we get a change in parameters. We have denser formation or higher resistive formation at greater depths, and lighter formation or lower resistive formation with higher porosity, more fluids in it at shallower depths. So now we have an isotropic inhomogeneous one. So it's inhomogeneous because the parameter changes with steps. But it is still isotropic because the parameter is the same in all directions. It just varies with steps. So as geophysicists, we are increasing the difficulty of our models. Then when we add shales to it or layering, we have some anisotropic homogeneous where the parameter is the same, but we add layering to it. That means that the parameter in vertical direction is usually higher than in the horizontal direction. That's called anisotropic homogeneous. And anisotropic inhomogeneous is when the parameter varies with steps. This is the realistic model, and we should always strive to model with this type of model, never with this one, even though as a student, you always start with this one. Here's an example. This is the size of a man. So this is about 2 meters. And this is an anisotropic layered formation. This is in Utah. And we see anisotropy at every scale. On the right side, we have an image log. This is an electrical image log. The yellow lines are sands. The dark lines are shales. And shales are very conductive. Sands are resistive. And we see this at a scale of 25 meters, which is reservoir scale. We go to logging tool scale, which is 3 meters, and we see the same layering in the anisotropy. We go to 2 feet, which is 25 centimeters, or even electron microscope images to 2.5 millimeters, and we still see the same layering. So anisotropy exists at every scale. We also measure anisotropy from the surface. Here we have a model which consists out of a 10-ohmmeter background, and we later will see what ohm is. Ohm is a measurement of the electrical resistivity. And then at 2 kilometers, we've added 2 oil-bearing reservoirs that are high resistive and 50 meters thick. So they are thin reservoirs. When we measure magnetic fields, we do not see it. The curves with or without the reservoir are the same. When we measure the electric field, we see this. So number one, we know anisotropy is important to electromagnetic measurement. And number two, we know that thin resistive layers can be measured with electric fields. So how do we come from these rocks to models? We start out with a scanning electron microscope image, which is in this case 1 millimeter. And we can see a bunch of grains. And when we stack these grains, then the space between the grains, also known as a pore space, is filled with fluids. Sorry, I have a hiccup. And these fluids in this picture, oil in red, and the black fluids here are essentially wetting the grains, and that means that the grains are water wet, which is the common case. So when we go and we translate this model to something that we can mathematically grasp, then we can define the model consisting out of small balls or spheres of a radius r, and this is the pore space. And when we stack them together like this, which is the most efficient way of stacking them, we can just take a quarter of it and calculate 2 pi r to the cube is a sphere minus 4/3 pi r to the cube, which is essentially the pore space, divided by the entire volume. And so then we can say that the maximum porosity we get is 0.48 or 48%. So if we have rocks that show us a porosity higher than 48%, then we know we don't have only primary porosity, but we have in addition to that fractures, because otherwise it could not be over 48%, because this is the most efficient model with the largest porosity. So Here, to review that definition again, we have the matrix with the grains, and this is the pore space. So the matrix fills a certain volume, and the pore space fills a certain volume. So the matrix volume is 1 minus the porosity, and porosity is the volume fraction. So a porosity is a dimensionless quantity, like 20% porosity means 0.2. We have primary porosity, which comes by unconsolidated deposits like rocks stacked together in that fashion. That's called primary porosity. And we have secondary porosity in so-called chemical rocks. Those are rocks that are cooked, like limestone. They're heated up, and the rock is in a solution, and then it gets baked again. And then the only way to get porosity is through fractures, because everything is baked in this hardened solution like carbonates or limestone. We also need to understand permeability. Permeability is a measure of the resistance a rock imposes on fluid flow. And if we have large flat grains, permeability is high, horizontal permeability 2000 millidarcy. Also, the ratio of vertical permeability to horizontal permeability is low. If we get smaller grains or flat lenses, then the ratio between vertical to horizontal permeability gets much larger. Here it is 10, here it is 16. So small flat grains give you a higher permeability. And here, and with large rounded grains, you have essentially very little permeability anisotropy. This is important for us to know. And when we go then and look at the electrical properties of a hydrocarbon reservoir, hydrocarbon being oil or gas, we look at a sandstone, and here we have a lens, and in this lens we accumulate hydrocarbons. And if we look at this in detail, then we can see that we have oil-bearing layers in this reservoir, tight zones where there is no fluids. Then we have an area that has oil, and this is mud invasion. And then we have an area which has mixed oil and water, and at the bottom only water. So we have many parameters to determine. And these parameters and resistivities get determined by borehole tools, normally known as lateral logs or induction tools. Induction tools induce a current, lateral logs inject the current into the formation. So these tools give us the resistivity. Why is it important to measure the resistivity? Oil is resistive, water is conductive. So it's extremely important to distinguish between that. Another effect that we have at thin resistive layers or hydrocarbon reservoirs is that we have charges accumulating at the high contrast boundaries. And this is known as a direct hydrocarbon effect, when we have an oil reservoir with charges at the boundaries. And there are various effects associated with these charges. But this is an anomaly that comes with thin resistive layer that I will mention several times in the future. So next, I will talk about the electrical properties, and namely about Ohm's law. And Ohm was in the 1800s a professor of physics at the University of Cologne. Actually, he was at the Jesuit college, but the University of Cologne at that time was not very active, and the Jesuit college became part of the University of Cologne. So Ohm's law says that the current we inject into a rock or a resistor is equal to the conductivity, or the inverse of the resistivity, times the imposed electric field. So sigma is the electrical conductivity, and the resistivity is the inverse of that. We also then have the chargeability of that rock. If that rock is thin, then we gets a certain chargeability, which is a relative permittivity or dielectric number. And then we have a vacuum permittivity times the electric field. And that's known as a dielectric polarization. These both play a certain role at certain frequencies. The dielectric polarization plays a role at higher frequencies and the electrical conduction at lower frequencies. How do we describe this? We have essentially an area A, and we inject the current from A to B, which is this side, and we measure then the voltage drop over a resistor. So the resistance that we measure is the voltage we measure between M and N divided by the current between A and B. And then normalized by the area over the length. So this is known as the resistance times length, or the specific resistivity, also known as apparent resistivity. So now let's look at some rock materials. We have on the left side quartz, which is very resistive, 10 to the 14th, and most rock minerals are very resistive. So that already tells us that the fluids are actually what make a rock conductive. And water has a resistivity of 1 ohm meters, and oil a resistivity of 1,000 million ohm meters and higher. And then salt water has a resistivity between 1 to 100 ohm meters. So salt water is important, brine and water is important in order to tell us something about the resistivity of a rock. Now, you've all heard about Archie's law, and Archie's law allows us to correlate resistivity measurements with porosity. So let me walk you through the thinking of Archie's law in the next 2 slides. So we have a rock, and the rock consists out of the grains and the pore space. And then the logic is that clean porous rock, no clay or any other conductors than pore water, the rock conductivity or specific resistivity is directly proportional to the conductivity of the rock or the resistivity. The rock conductivity is only controlled by the water conductivity, and thus the water is called conductor water. If we have a water saturated rock, that means the rock is completely water saturated, then the base resistivity of that rock, the R0, is directly proportional to the resistivity of the pore fluid. Now, in order to equate this, we have to introduce a proportionality factor, and this proportionality factor is called F. And F is nothing else than the fully water saturated rock divided by the resistivity of the pore fluid. And this factor F is called a resistivity magnification. It is called a magnification because the resistivity of the grains and the water saturated rock is always higher than the water saturated, the pore water resistivity itself. And F can also be a proportionality constant divided by the porosity to the power m, where A is called and M are cementation factors, and they need to be derived empirical from graphs like this, which are measured. And then you get these. In most cases, they are 2. Some cases 1.9, certain reservoirs, but they don't change much within a reservoir. Now let's talk about partial water saturation. Partial water saturation we have when a rock is partially saturated with hydrocarbons and then with water. And in partial water saturation, we introduce the resistivity RT, which is a true partial water saturated rock. And we can say RT is nothing else than a different proportionality factor times the fully water saturated rock. And then we have this I, which is also called a resistivity magnification. But this is a resistivity magnification by the non-conducting pore content, oil and gas. It also depends on water saturation itself. So we have two factors that we can play with. Now, we are now going over to borehole measurements. Because there's a lot of things to remember, I'll give you the opportunity to ask one or two questions at this stage, if you like. Just unmute your microphone. And
ya, oke, good. Oke, ada yang bertanya?
Professor Andre, we cannot see your head.
Sure, you can see my hair now.
You were sleeping.
No, really. Oke, ada yang bertanya? Bisa bertanya bahasa Indonesia ya, nanti saya translate. Ada nggak? Oke, oke, please. Ya.
Pak, mungkin ini bukan pertanyaan, cuman sekedar mau ini, Pak.
Oke, ya Erika, go ahead.
Bukan nanya tentang materi sih, Pak.
Oh iya, silakan ya.
Tadi ada kelewat. Ini bahasa apa, Pak? Inggris atau Indonesia?
Terserah aja, bahasa Inggris saja. Oke, nggak apa-apa kalau bisa ya. Silakan, please.
What was the question, Andre?
Okay, I think he's gone. Okay, she has.
Erica is still there.
Erika. Okay, go ahead, Erika.
I can't see the chat.
Excuse me, sir. So let me introduce myself before. My name is Erika. My student ID 120120044. So I want to ask something about the password of the inbox. Can you repeat once more the password, because I'm not too much here. Thank you, sir.
Okay.
Andre, I didn't understand that.
He asked actually about the password for the library. So yeah, I will give them actually. Okay, don't worry. Okay, Erika.
No,
yeah,
I can explain that. Just give me the question.
Okay, so she asks about how to log in and then what the password for the EM materials.
It's EM book as username, and that's the resource library, and the password is great year. GREATYEAR, great year.
Okay, you can see in the chat.
Okay, I can't see the chat. So okay, and no questions, and I go on.
Okay, any more question? Ada lagi yang mau bertanya? Ada? Bisa bahasa Indonesia ya, nggak apa-apa ya. Kalau ada yang bertanya, mungkin ada yang bingung dari slide-nya tadi. Silakan. Yakin ada yang bertanya? Okay, cool. Maybe can you explain more about the resistivity, because maybe they also they actually learned before in the before these lectures about the resistivity measurements, and the resistivity actually not only from the porosity and then permeability, but it's also of the content of the like the how can I say electrolyte in the materials. For example, the minerals inside the water. Yeah, you might can do you have any idea how to explain that to them? Okay, thank you.
Yes. I believe we will get to that at some stage, but let me explain it to you. As Archie's law says that the resistivity of rock is directly proportional to the resistivity of the pore fluid. Pore fluid, which is all of the pore fluid. If you have more salt material in the water, then the pore fluid is more conductive. So sweet water with low sodium content is 1 ohmmeter. Seawater with high sodium content is 0.3 ohmmeters. So the variation depends strongly on how much salt concentration you have in it. Now, obviously, minerals themselves and clays also play a role, but the pore fluid itself is primary conduction. Secondary conduction would be surface conduction, and then the minerals themselves is a kind of tertiary conduction if you add minerals to it. But the salt itself in the brine is quite important. Okay, does that answer your question?
Yeah, another one, I mean, for example, in the exploration is like the gold explorations, how the EM method, I mean, can be involved. As you explained, it's just for I mean, in this case, it's not in the water content. I mean, it's not related to the water, but it's related to the mineral itself. For example, gold or another rare
Yes,
minerals.
it's related to the mineral.
Yeah.
And usually minerals, rare metals or metals are conductive. And so when they are dissolved in water, they are also the cause of free electrons that flows and a lower resistivity, higher electrical current flow.
Okay, thank you, Pierre. Yeah.
So is anthracite, coal. So high carbonification of coal seams gives you a very low resistivity. Lignite is highly resistive.
Yeah, I agree.
Okay, so now the first measurements were done by the Schlumberger brothers by putting transmitter injection, current injection in the bottom of the hole, and then having some voltage electrodes which they move up. And this is where the word log comes from, because they're pulling this up the borehole and they're writing a log. And they use 3 insulating wires. This was done in the 1920s. And they injected a current through the bottom, and the return electrode is at the top. So here we're now summarizing the parameters we used in the Archie equation. RT is the virgin zone, the resistivity of the undisturbed rock formation. And RXO is the resistivity of the mud invaded zone. The drilling mud goes into the porous zones and invades it to a certain amount. RM is the resistivity of the drilling mud. And then we have shoulder beds, our shoulders at the top and the bottom, which we also need. So all of this requires that we have many parameters with different resistivities, the mud system, and we have different resistivity tools. And these tools vary by service company. So what we have is we have a frequency dependent of the electrical methods in the borehole. We have DC methods like what the Schlumberger brothers used. And we have high frequency methods going up to gigahertz, which are used for imaging tools. But normal logging tools use 20 kilohertz. And 2 megahertz tools are dielectric tools. So the physics here is in the DC method, conduction. In the 20 kilohertz, we have induction, and then higher frequencies, propagation tools. The parameters we measure in the conduction case are resistivities, conductivities, and dielectric constant. And the tools are case hole tools and open hole tools. And the rest of the names are not so important. You have then the different names of the tools, normal tools and induction tools, dielectric tools. All of these tools are active tools. And then there are as only passive tools, self-potential tools. And self-potential tools give you an idea about the porous zones, because the higher the self-potential, the more fluids you see.
Kurt,
Now,
can you, Kurt, sorry for interruption. So can you explain more about the frequency of the DC and then I mean the induction and conductivity, what the range in this case, so they can understand.
most induction tools operate at 20 kilohertz. So this is an induction tool which induces through time varying fields a signal in the subsurface. And the DC tools are direct current injection. You inject the current and then you measure the voltage in response to that. And for dielectric tools, you consider the wave propagation.
Okay.
Dielectric tools only work in high resistive environment. So let's talk about lateral logs, current injection tools. Current injection tools work by injecting a current in one electrode in the ground, and then through side electrodes, you inject the current of the same polarity. And we know that positive charges from magnets, they are pushing each other. They are not attracting each other. So this is known as focusing. So when you push the current to a smaller area into the formation, then you're focusing it. And the LL3, which has 3 current injecting electrodes, was the first focusing tools in 1949. The LL7 came a few years later, and they controlled the current they're injecting through these side electrodes into the formation by measuring the voltage across these black ring electrodes such that it became 0. So they inject a higher current until this voltage becomes 0, and you do the same for this side. And this way you are squeezing the current at the center electrode together. And then what you do is you measure the current at the center electrode and the voltage, and you get a measurement of resistance or an apparent resistivity. Now, the old way to do this is to focus these tools. And this is shown on the left. Those are the limits. There are problems with these tools in deviated welds. I keep blaming this on my Apple computer with the shifting of the PowerPoint. And then I realized that it has to do with my mouse. But in the past few shifts, I didn't touch anything. So I don't know why this PowerPoint on Apple always shifts so many times. So then a new way, which includes geophysics, is you simply inject the current and you let it flow wherever it goes. And you measure the voltages on a multitude of electrodes. You measure the voltage with respect to a surface return. You measure the voltage between electrodes, and you measure the second difference or the derivative of the voltage between 3 electrodes. And this second difference is a direct measure of the current leaking into the formation. You then get raw data and you use inversion by modeling the tool to obtain the resistivity of the formation. That is a much more accurate way of measuring borehole resistivities. Now, Schlumberger then, after that tool was built their own version of it, and they used focus measurements, and they have different, differently spaced arrays. And you can see here that the near arrays are pushing the current into the formation, and you measure this range. And then the distant arrays from here to here are essentially measuring a larger voltage, but you still push the current in it and you still focus the current. So this is a focused array tool. And the same can be done with induction logging tools. In induction logging tools, you are relying on closed loops generated by coils, and the coils are in the transmitter and the receiver. So each of this is a coil, and you have two transmitters or three and two receivers, and you measure the distance between them. And the original tools were 40 inches distance between transmitter and receiver. And the new tools have multiple transmitter and receivers shown on the right. This is the array induction logging tool, which was originally invented by the British plasterboard. And then Schlumberger made their own array induction out of it. And then Baker built theirs. So this is how they work. You have essentially a coil, and you know from Lenz's rule that the induced currents have the same direction as this loop. And then you measure at receiver electrodes and use two receiver electrodes because you measure in a balance point. They're wound in opposite direction. So you measure no signal unless you have a conductivity variation. So you calibrate this tool in air in a high resistive environment, and then you run it in the formation. And in the array tool, you have one transmitter and multiple receivers, and you get more measurements. The more measurements you have, the more parameters you can derive. And as I said before, we have many, many resistivities to distinguish in the borehole. But when we only get 2 or 3 measurements, we can only find 2 or 3 parameters, but we need 7 parameters. So this is very difficult to do. And that's why the new logging tools have many, many more measurements, and they became array tools. Here is an example of the numerical modeling exercise. We have the borehole in green on the left. We have a standard 10-ohm formation in red. And then we have different mud invasions of different thickness and depths. And we measure deep and shallow arrays. And you can see the deeper, the shallow arrays are in red, and they see the fine layering, and the deep arrays see none of the layering. So what you can then do with some filtering techniques, you can take the layering from the shallow tools and impose it on the deep tools so that you then have resolution matched measurement where the deep measurement also includes the shallow layering. How do we know that these tools work better? Here's an example for an array induction logging tools. We comparing an old tool. This is the DPIL dual phase induction log with a high definition induction log in blue. And you can see the measurements, see higher resistivities. That's because of better electronics. And the higher the resistivity is, the more oil you find. You also see more zones. So you have oil-bearing zones here that you wouldn't see with the old tool. And you define a cutoff percentage and you calculate from the resistivity values and the cutoff value how much oil you have in the ground. And here you can see that the array induction sees 24% more oil initially in place. So improving the logging tools and adding geophysics to them gives you more oil. And that is always the case because oil is resistive, and finding more oil means getting more signal out of a resistive zone, out of the noise. And so the more you improve the logging tools by either better electronics, better filtering techniques, modeling and inversion, the more oil you find. So applying geophysics to the log environment always finds you more oil. So being a petrophysicist is a very secure job for you. So if you want to get a job in the industry, prefer a petrophysics job because petrophysicists never get laid off. We are now going to anisotropic logging tools, anisotropy tools, or 3D induction logging tools. And again, let me repeat the anisotropic formation that we seen before. And here is an example from Shell that they published in the early 1990s. They drilled a well, and we have here the resistivities. Usually high resistive zones mean oil-bearing zones, low resistive zones mean water-bearing zones. And so the oil is here, and this is water. So they thought this was right, but then they noticed that they have very high gamma ray, and gamma rays are usually measuring how much shale you have. And when they caught it, they saw that the sands had a huge amount of oil in them, but the shales would dominate the measurements because they would only see the horizontal resistivity, because they only would inject horizontal induction currents. They would only induce horizontal induction currents. So then they did a production test, and they saw that the zone that usually they would have interpreted as water lag had a huge amount of hydrocarbons in it, and gas in this case. So the problem was known from the early 1980s, but it was decided that it was not possible to build a tool. Shell in 1991 realized that they're missing 20 to 30% of reserves. And then they started a project with Baker Atlas and built a logging tool. And since 1999, they have been running that tool with great success. So the anisotropy tools for Schlumberger and Baker are making them a lot of money. So these are the results from the 1986, where you can see these laminations, but you can't really see them and can't understand them. And essentially says you can't do this. But when you then go and add to the horizontal coils, to the vertical coils, horizontal coils, then you are inducing induction currents in this direction. And these induction currents can see the high resistors in the sands, and the vertical resistivity is always higher than the horizontal. And by having three transmitter and receivers, three component transmitter and receivers, you can measure the vertical and the horizontal resistivity. Next, we will look at an example from test measurements. Where's my cursor? There we go. And we see here the horizontal induction currents and the vertical induction currents. The sand has high resistivity and the shales low resistivity. The gamma ray is higher in the shale zones. And here we have the horizontal resistivity. When we now add the vertical resistivity, we see here we have significantly higher resistivity, and we see also more high resistive zones. I'm sorry, the horizontal resistivity gives you already higher resistivities. And when you add the vertical resistivity, you get significantly higher resistivity values. From the literature, and the left side is a Baker tool, on the right side is a Schlumberger tool. Both are adding more water saturation from the vertical resistivity here in orange. The yellow one is only from the horizontal resistivity. Here, the red is from the horizontal, and in orange is from the vertical resistivity. In both cases, they are finding 40% more oil in the same well. So they're essentially earning millions of dollars for each well where they apply this tool. The next example is about through casing resistivity. And we are almost done, 3 or 4 more slides. And through casing resistivity works by injecting a current into this casing. And the casing is 1 million times more conductive than the formation. And the current gets injected and leaks into the formation. We then measure the voltages and the difference between the voltages, and the difference between the current flowing along the casing here and the current flowing along the casing there, according to Kirchhoff's law, is the current going into the formation. So if we can measure 1 million times smaller signals, we can measure from inside the casing through casing. So it's in principle a very simple measurement. But it's very complicated. It gets to the limits of logging tool design. Here is an example for Baker and Schlumberger through casing measurements, Schlumberger being blue, Baker being red. This is the original induction log. And you can see that it sees much finer layering, but it's very close to induction log. And the induction log was run before the casing was set. That's why there is a difference. But essentially, you can see that through casing resistivity works. If we look at the overall design in logging tools, we can say that the voltage measurements for lateral logs are in the millivolt range, for induction tools in the microvolt range, for through casing resistivity tools, nanovolts, and for deep reading electromagnetics that I will talk about in a minute, it is in picovolts, below sub-nanovolts. How do we extend the borehole measurements to the surface? In the first instance, we use crosswell measurements where we have one transmitter. The transmitter injects a current. We have a receiver. We measure the current. We measure the voltage. And we plot a resistivity along the path between the transmitter receiver. Then we move the receiver up, do the same thing, plot another ray, and we move then the transmitter. And with many of these, we plot at these intersecting lines, many resistivity values, we average them, and we get a colorful resistivity tomogram. So this is how Crosswell works. Here's an example of field data from the Devine test site in Texas and synthetic data. And this is more improved synthetic data. Now, there are other ways to understand that we need different logging tools. This is the standard logging tool on the right side with an average depth of penetration of 3 meters. So if you have a borehole, you sample only 10 to the minus 13% of the volume of the reservoir. So if you can make deeper reading tools that look 200 meters into the formation, then this is really good. And here is an example of such a deep reading tool we built a prototype for. And this is used for horizontal wells. In a horizontal well, you drill a well, you produce oil, and when you produce oil, you suck up the water. So you want to see the water encroaching on the borehole to shut it off, because once the water reaches the wellbore, it destroys the reservoir and the production. And so here, distances of the oil-water contact between 1 to 50 meters modeled, and we can see these curves are significantly different. So we can see water coning in the well, but the problem is that we need 13 decades of dynamic range. So we built a tool and we went through an exercise and used all kinds of techniques to overcome this threshold of measurement. And here is an example of real data. So we clipped the data at early times, and we have here the field data in black. And we have a formation which is conductive about 10 meters away, a formation that's resistive 30 ohm meters in green, and the 1.5 ohm meters, which is blue, is the one that matches the data best. So we can actually look sideways. And here are some pictures from the tool at the test site, which is on the beach. The tool was used in multiple modes. This is the transmitter. These are the different receivers. It was used vertical and horizontal. And the earth was simulated by the sand on the beach. And the resistivity contrast was essentially the groundwater at 11 meter steps. So what we learned is electromagnetics is important for well intervention, geothermal and special minerals. The resistivity contrast gives us rise to various responses. and we need to use different logging tools to evaluate the reservoir. Linking the surface to the borehole is key to get the best value out of surface measurements. And with this, I am opening the floor for more questions.
Oke, thank you, Kurt. Ada lagi yang mau bertanya? Silakan.